let us consider another example which will highlight a very useful skill of sketching polar curves. And so we will try to sketch the curve r equals 1 plus sine theta. Here, as explained above, we can assume that theta is between 0 and 2 pi, because that is the period for the angle theta. If I add 2 pi to theta, I add up at the same point in the plane as the one I start with. And so to sketch this curve, I will first need to draw the auxiliary graph of the dependence of r on theta. So what that means is I will use rectangular coordinates again, and I will draw r and theta as if they were functions of each other. Well, as if r were the function of theta, which is by this equation we have over here. And so what this equation tells me is I must draw the graph of sine theta and then shift it upwards by 1. So let's start with the equation of the graph of sine theta. So if this were 1, this corresponds to the r value of 1. This is the minus 1. And I'm looking at thetas from 0 to 2 pi. Let's see. So this is my 2 pi over here. Pi over 2, pi, 3 pi over 2, and 2 pi. And the maximal value my sine theta can take is 1. And so this means that 1 plus sine theta can take the value of at most 2. Right. And then I'll just need to draw the graph of sine theta shifted by 1 upwards. So it means it will be contained between these two lines, between the coordinate axis and the line r equals 2. And so as I start, at theta equal to 0, here I have r of 1. And so it grows up to r equal to 2 at theta equal to pi over 2. So I have curve doing something like this. Then, so in fact, let me draw the line r equals 1 here, just to guide me in sketching this graph. Okay, so then I have one plus sine theta go from 1 to 2 here, like so. And then from pi over 2 to pi, it goes back to 1. Because sine theta is 0 at pi. Then at 3 pi over 2, I get down to 0, because sine theta is minus 1 at 3 pi over 2. Let's see. and finally it comes back to 1 for theta equal to 2 pi, like so. Okay, so this is the rough sketch of my dependence of r on theta. Now, what is its purpose? Well, it's just supposed to guide me in drawing in the polar plane. So now let me look at the polar plane. This is nothing but an auxiliary graph, right? This is just r as a function of theta. Now I have to use the actual polar plane. So this here is the polar axis. Which I have placed so that it coincides with the x-axis. And so what I will start with is I'll draw the intercepts that my curve has with these axes. So for this direction, which corresponds to theta equal to 0, I have r equal to 1. Right here I have to put a point that has coordinates, that has polar coordinates of 0, 1. So that's theta equal to 0, r equals 1. Then for this direction, where theta is pi over 2, I have the value of r of 2. So I'll have to put a point somewhere here on this axis. Then for this direction, which corresponds to theta equal to pi, I have the point with, again, r equal to 1. So I have a symmetric point to this one here. So this is the point 1 pi. And finally, for theta equal to 3 pi over 2, which corresponds to this axis here, I have r of 0. So my intercept will coincide with the origin. So then what my curve does here is the following. As theta goes from 0 to pi over 2, the radius grows from 1 to 2. So it does something like this. And then as theta goes from pi over 2 to pi, here my radius goes down to 1. And then further on, let's see. So these two halves should really be just symmetric. So they are not exactly symmetric in my picture, but yeah, something like that. And now from this direction to this here, my theta varies from pi to 3 pi over 2, and r goes down to 0. So that means my curve winds into the origin. And then finally, between 3 pi over 2 and 2 pi, which corresponds to the fourth quadrant, my curve goes back from the origin to the value of r equal to 1. And so this is the rough sketch for our curve. R equals 1 plus sine theta. And so this curve, in fact, has a name. It's called cardioid. Apparently because it somewhat resembles the heart shape. I guess if you look at it upside down or squint your eyes enough. Now, another way to define this curve, a purely geometric way to define this curve, is the following. You can take two wheels of the same radius, so say one wheel and another wheel, the same radius, like so. And if you fix a point on one of the wheels, say this one, and then let the wheel roll around, say, let the right wheel roll around the left one, without sliding. So it rolls with it touches here the left wheel and it rolls around it like so. Then the trajectory of the red point will be of this form. So that's a geometric way to define such a curve. Now, again, I will leave to you as an exercise sketch the graph of r equals 1 minus cosine theta. And so you can proceed in the same way, first sketching the dependence of r on theta and then drawing in the polar plane. And you will actually obtain another cardioid, or if you want to think of it this way, the same cardioid but with a different orientation. So that's an exercise. Now, going back to this graph I obtained here, I would like to verify that this is indeed the correct graph. And so a good way to do this will be to use Sage Math. And so for that, I will go to my terminal here. I will start Sage, like so. And so there happens to be a polar plot routine in Sage. So I do remember that there is such a routine, but I do not remember how to use it. So what I will do is I'll go to polar plot and I will put question mark, enter, and Sage will tell me how to use this routine. So now I can just copy, say, this command here, go back to the Sage plot prompt, and in the prompt I'll paste this command with replacing the function by our by the function for our cardioid. So it's 1 plus sine of x. So you see that here Sage denotes the angle by x, and the angle will vary between 0 and 2 pi. As we know, that's okay. That captures the entire curve. And so I'll plot my polar curve here in blue. And so here's my curve. And as you see, if you compare this curve to the sketch we had, so the sketch doesn't look terribly unlike this, the actual graph here. And so this gives me a convenient way to check that indeed my graph was, the sketch of the graph of this curve was correct. So you can deal with with sketching pretty much any polar curve in the same way. So first you will want to sketch the curve in the plane, in the r theta plane, just to visualize the dependence of r on theta, see where the r is increasing, where it is decreasing, and so on. And so then using this information, you'll be able to graph the intercepts in the polar plane. And then based on those, you can go on to find the rough shape for the graph in the polar plane itself. So using the sketch of dependence of r and theta and the intercepts, you can then roughly sketch out the shape in the polar plane. Occasionally, you may want to take into consideration other angles as well. So for example, you're not happy with just knowing the values in the quadrants. You may want to know also the values on bisectors of the quadrant angles, like so. In our case, these are not interesting angles, but in general, if you have a more complex curve, you may want to determine values of r that correspond to these four bisectors and so on. So the faster oscillating your polar curve is, the more refined you will have a partition for theta. So like here, for our curve, it was enough to consider partition with intervals of length pi over 2. You may want to look at finer partitions if your curve oscillates faster than this.